Hello everyone and welcome back. My name is Mr. Kovalt, and in this video I'm going to be going over kinetic molecular theory and the properties of gases. And in this particular video I'm going to be talking about how the kinetic molecular theory relates to certain gas laws. I'm not going to cover the ideal gas law. I'll do that in another video. So let's get into this. So the first thing we need to talk about are the properties of gases. So what are the properties of gases? Let's remind ourselves. So gases are able to expand completely to fill their container. The reason for that is because gases are particles that are spread out very far apart from each other. So there's the attractive forces, the intermolecular attractive forces are not able to act on those particles because they're so far apart. And so they are free to move and expand into any space available. So that is the first property of a gas. The second one is it takes the shape of the container. And again, that's related to the exact same thing, right? So no matter what the shape of the container is, the gas will fill and expand to take up that shape of the container. This is different from liquids where the particles are closer together such that the intermolecular forces are able to attract and then keep them relatively close together, so that they kind of stick together for the most part. Although they are able to move past each other, they don't move far from each other like in a gas. So when you put a liquid into a container, that container also will have the same shape of the container, but it will not expand and fill up the container itself. So it's not going to take up the shape of the whole container. The other thing is that gases have very low density. That's because density is the mass per volume, right? So you can have a certain amount of gas, and so that's going to take up a certain volume, and gases tend up to take up the volumes of their containers, which are pretty large. And so they have a lot of space between the particles. And so density is basically how much space do you have for a given mass. And so because the particles are so far apart from each other and they're able to expand away from each other, this gives gases a very low density as compared to solids and liquids. And so that brings up the next point of being compressible. So if there's a lot of space between the particles, then you can squeeze them and reduce that space. So you can compress them and make them come closer together. So that explains why gases are highly compressible, whereas solids and liquids are virtually not compressible at all. And then finally, we have mixtures of gases. So whenever you have mixtures of gases and you put them together, they're always going to be homogeneous. They're always going to be completely mixed together. You're not going to have more of one gas on one side versus another gas on the other. They're going to be completely mixed. And again, the reason for that is because the particles are so far apart from each other, they're not really interacting. And so they can spread out and fill up the container. So both gases, if you mix 2 or 3 or 4 gases, all of those gases can expand evenly throughout the container. And so therefore they're always going to be homogeneous. And then last but not least, fluid. So gases are fluid, meaning they flow. So like other liquids or other fluids like, liquids or, like water, they flow. So does gases. Gases have a kind of a fluid nature to them. The fluid dynamics can be applied to gases as well. And so that's the last property of a gas I want to go over. The next thing I'm going to go over is kinetic molecular theory. What are the postulates of the kinetic molecular theory? So that's next. So give me 1 second. Okay, so let's talk about kinetic molecular theory. So there are 3 main postulates for kinetic molecular theory. The first one is that the size of a particle is negligibly small. That means that we assume it's pretty much zero. That basically is uh, the assumption that the particles occupy a negligible volume even though they have mass. So we're assuming that these particles have mass, but they're negligibly small, practically zero. And so under normal conditions, normal pressures, uh, the space between the particles is so much larger than the size of the particles themselves that this postulate is justified under those conditions. So, but as I said before, under extreme conditions like very high pressures, where you're putting a lot of particles in the same space, um, or if you're reducing the size of the container or you're reducing the volume of the container, squeezing particles together, under those conditions, it wouldn't be the size of the particle would no longer be negligible because you're reducing the amount of space between them. So when you're comparing the space, the overall space of the container between the particles, uh, compared to that of the size of the particles, they become closer together, and so this postulate would not apply under those extreme conditions. But under normal conditions, the particles are so far apart that the volume taken up by the actual individual particles is so small compared to the actual space that the gas is occupying. Okay, so what about the second one? So the second postulate is that the average kinetic energy of a particle is proportional to the temperature in kelvins, right? So average kinetic energy of the particles is going to be proportional to temperature. And so again, this makes sense because the motion of the particles is due to thermal energy. So you put more thermal energy into the particles, they're going to move faster and they're going to have a higher kinetic energy. So the motion of the particles is due to the thermal energy, and this energy is distributed among all the particles, right? So all the particles together are going to have a certain amount of energy, and so when we talk about kinetic energy of the gas, we talk about the average kinetic energy of the gas, because different particles are going to be moving at different speeds. And so we need to take an average of that. And so the thermal energy is related to the average kinetic energy of all the particles in the gas. So that's what I have here. So some particles are moving faster than others. And so they're going to have, each individual particle is going to have a different velocity, or they're going to have therefore a different kinetic energy. But we're taking the average of all those, and that's going to be proportional to the temperature. Okay. And one thing to note is that kinetic energy, which is 1/2 mv squared, you calculate the kinetic energy by this equation here. You'll notice that kinetic energy is related to velocity squared, not velocity. Uh, so kinetic energy, not the velocity, is proportional to temperature. So don't make that mistake. Yes, velocity and kinetic energy are related, but it's the average kinetic energy that is proportional to temperature, not velocity. And we can see this in this example. So you have a sample of you have a sample of argon and a sample of helium, two different gases. They have different masses. So both of these samples of gases are going to have the same average kinetic energy at the same temperature, right? But they're not going to have the same average velocity because, again, the average kinetic energy is related to the mass and the velocity squared. So helium is a smaller particle. So to have the same kinetic energy as the massive argon, it's going to have to move faster because we're multiplying mass times the velocity squared, right? So argon is going to have a slower average velocity, and helium is going to have a faster average velocity. Their velocities are not going to be the same. So average velocity is not going to be proportional to temperature, but average kinetic energy is. Okay, so one more postulate. So postulate number 3 is next. Okay, so the final postulate is number 3. The collision of one particle with another, or of the particles with the walls of the container, is completely elastic. So what does it mean for collisions to be elastic? Well, what that means is that when the particles collide, they may exchange energy, right? So energy can be transferred from one particle to another, but there is no loss of that overall energy of the system. So what does that mean exactly? It means that there's no stickiness of the molecules. The molecules are not going to stick together when they collide. It's not like you have Velcro balls and you throw the Velcro balls together and they collide and they stick together. That doesn't happen. So what happens is so basically what I'm saying is that the particles do not exert any forces on each other. So we're assuming and ignoring the intermolecular forces that actually exist between particles. And we're going to assume there are no forces between the particles. So when they collide, they bounce off from each other without sticking together or loss of energy. And also, there's no deformation of the particles when they collide. So basically, they're like billiard balls and not lumps of clay. So you throw two lumps of clay together, they'll collide and they'll stick together. They'll deform, right? They'll flatten. But for billiard balls, right, they collide. The 8 ball collides with the cue ball, and so they just bounce off of each other and they don't stick together, right? So that's what we mean by collisions being elastic. So we're assuming all of this with regard to the particles of a gas. And so next we're going to talk about how this relates to the properties of each gas. How can we relate the kinetic molecular theory to explain what we observe about gases? So let me, before I go on to that, let me remind ourselves the difference between a law and a theory. So here we're looking at Avogadro's law, right? So the gas laws, for example, Charles' law, Boyle's law, Avogadro's law, Gay-Lussac's law, those are all laws. And what a law is basically a description of what we see in the world around us. It's what we observe, right? These are statements of observations of relationships between things, right? So the relationship between the volume of a gas and the pressure of a gas. What do we observe? What are the general observations we make? Those are laws, but they don't explain anything. There's no why behind it, right? The laws don't explain why the laws are there. That's what the theory does. So the theory explains the observations. So when we're talking about kinetic molecular theory, that we're using the theory to explain the laws themselves. Why do we see that when you raise the volume of a gas, the pressure of the gas goes down? Why is it inverse? Well, the kinetic molecular theory can explain that. So that's what we're going to get into next. Okay, so before I get into talking about the different gas laws and how the kinetic molecular theory can help us understand the gas laws, let's go back and talk about the properties, the gas properties that we talked about before. I know I explained a little bit about it, so let's just go over it quickly again, and I'll fill in some things I didn't say before. So when we're talking about, say, pressure, so one of the properties of gas is that it has pressure. It puts pressure on containers. And so the reason for that is we got to go back to this equation here. So this equation is the equation for pressure. So pressure is equal to an amount of force that's applied to a given area, right? So let me use a couple of examples. So one, take snowshoes, for example, right? So why do we wear snowshoes in certain areas where there's a lot of snow? Well, the reason is because we want to distribute our body weight, which is a force, right? We have our body weight is a force acting on the ground, right? So our body weight, like me, I'm 165 pounds. That is a force that is being applied to a particular area, which is the bottom of my shoes, right? So when I'm walking in the snow, if I'm not wearing snowshoes in certain circumstances and the snow is deep and not very hard or compact, then I will fall through the snow, or the pressure of my body will push the snow down, and I'll go through the snow, and it could go up to my waist, right? I don't want that to happen, right? So in that case, the soles of my shoes, the bottom of my shoes, is a relatively small area on which the force of my body, the weight of my body, is acting on, and so that means that the pressure is going to be high, right? Small area, large force, large body weight leads to a high pressure. So I'm putting a lot of pressure on the snow, and I'm going to sink into the snow. If I wear snowshoes, the snowshoes that I connect to my regular shoes or whatever boots I'm wearing, that has a larger surface area. So I'm increasing the amount of surface area that the force is acting on. So if I increase this and keep this the same, my body weight's still the same, then I am decreasing the pressure, and so therefore less pressure on the snow, and I'm less likely to fall through the snow, and I can stay on top of the snow. So that's why we would wear snowshoes. Another example would be the pressure felt like if I'm dancing with someone and they're wearing stiletto heels, or they could be wearing platform shoes, right? So, which one would I prefer to have my toe stepped on? Probably neither, but if I had a choice, I would choose the platform shoes because, again, you have a larger area and compared to the stiletto heel, which has a very tiny area. So, more less area means more pressure, and therefore, step on my foot with stiletto heels, it's going to be very painful. I'm going to feel a lot of pressure. So that's kind of a couple of examples how pressure works. So if we think about that in terms of particles, we have particles that are moving around constantly in our container. And so when those particles hit the side of the container, they're applying a pressure, right? So it's like if I took a tennis ball and I throw it against the wall, when it hits the wall, while it's in contact with the wall, it's applying a force to the wall, right? So now if I'm thinking of the container as a surface, right, the inside of the container, the surface area of the container, I have all these particles moving around, and at any one instant, I have a bunch of particles hitting up against the side of the container, and at that moment, they are applying a force to that area of the container. So if I think of it in terms of that, then the number of particles that are hitting up against the side of the container at any one moment is going to apply a total force to the inside of the container. And of course, the inside surface area of the container is the area that is the force is being applied to. So you can see how pressure is going to be related to the movement of the particles in a container, and how that might also be applied or related to the volume of the container. Larger volume means larger surface area, smaller volume means smaller surface area, and things like that. So that's how you can understand how the pressure of a gas works inside of a container related to kinetic molecular theory. What's going on with the particles? We have these particles that are moving around pretty fast. They're hitting against the walls, applying a force to the walls. The walls have a certain surface area, and so therefore that's going to apply a certain pressure to the container. Oh yeah, what about indefinite shape and volume? So indefinite shape and volume I talked about before. Because the particles of the gas are moving around so quickly and so fast, and they have a high kinetic energy, a relatively high kinetic energy, that kinetic energy will overcome the attractive forces. So when they're not going to be attracted and pulled together like you would see in a solid or a liquid, right? So with a solid or liquid, the particles are not moving as quickly, so the intermolecular forces can attract them and pull them together and keep them together. That's not so with a gas. So with a gas, the particles are moving pretty quickly at normal temperatures, and so because they're moving so quickly, they have a high kinetic energy. The intermolecular forces can't really act on them, and so they can spread out and fill in the shape and volume of any container, any space that they're open to. So that's indefinite shape and volume. Compressibility I talked about before, because there's so much space between the particles, you can easily squeeze them together and make them come closer together in that space. So, and again, that leads to the reasoning behind this number two here. Again, they have a relatively high um, kinetic energy. The intermolecular forces don't really work on them, pulling them in. So you can squeeze them because they have all that space between the particles. You can decrease the volume and compress the gas particles closer together. uh, Low density, that is related to, again, the amount of space between the particles. So because you have such a small mass, you can have such a small mass of a gas, and because any amount of gas was going to fill out any space, right? So I can have a very tiny amount of gas in terms of mass, but that could fill in like a whole room, if you will. So that is the reason behind the low density of gases. And then finally, we can talk about how density and pressure are related to each other. So if I have a container with particles in it, then I have a certain density with regard to the mass of the gas that's in the container and the volume of the container that it fills out. So that is how density of a gas is found. So it's the mass of the gas and the volume that the gas is taken up. Now, again, remember that the pressure of a gas is due to the particles hitting up against the sides of the container. So if you increase the amount of particles in the container, right, you're going to increase the density of the gas, right? Because you're putting more mass, more particles, more mass inside the container. So mass is going up, and you're keeping the container volume the same, right? The volume of the container isn't changing in this example. So by putting more particles into the container, I am increasing the density of the gas in the container. But also, because I'm adding more particles to the container, more particles are going to be hitting up against the sides of the container at any one moment than before, right? So now that I have more particles hitting up against the side of the container, I have more force hitting up against the side of the container, because the amount of force that the particles are going to be exerting is going to be greater because I have more particles that are exerting forces. So the sum of all the forces of the particles increases, right? Because I'm adding more particles to the container, and therefore, if I'm adding more particles, therefore more force, and therefore more pressure. So the surface area of the container doesn't change because the volume doesn't change, but I'm increasing the amount of particles, and therefore the amount of force, and therefore pressure increases. So if the density of the gas increases, then the pressure of the gas increases as well. So that's it for the properties of gases being explained by kinetic molecular theory. Next, I'm going to be talking about and explaining the gas laws by the same theory, kinetic molecular theory. So stay tuned. Okay, so now let's apply the kinetic molecular theory to the gas laws. So let's explain these gas laws according to kinetic molecular theory. So let's start with Boyle's law. So remember, Boyle's law is P1 V1 equals P2 V2. And this is basically saying that the pressure and volume are inversely proportional. If one goes up, the other goes down, right? So why is that? So if we remember pressure is due to the number of particles that are moving around constantly, hitting up against the sides of the containers, right? So more surface area, then less pressure, because the larger the surface area, remember, you still have the same number of particles in the container. So if you increase the surface area of the container, then less particles are going to be hitting up against the sides of the container at any one moment, because there's just so much more space. So therefore, less pressure, right? You decrease the volume, therefore, more surface area for the, just a moment. Sorry about that. So you decrease the size of the container. There's less surface area for the particles to hit up against. So more particles are going to be hitting up against the side of the container at any one moment, and therefore pressure increases. So that explains why there's this inverse relationship between pressure and volume. What about Charles' law? So remember from the kinetic molecular theory, the temperature of the gas is related to the average kinetic energy, which is then tied to the velocity and movement of the particles. So higher temperatures is going to mean that the particles are going to be moving overall, on average, faster. Well, what happens when you throw a ball harder against the wall, right? If I take a tennis ball and I throw it harder against the wall, as it's in contact with the wall, it's going to apply a larger force. So the forces of the particles increases because their velocities increase due to the increase in temperature. Well, what is that going to do to a container? Well, think about an elastic container like a balloon, right? So if the container walls can move and you're applying a greater force against the outside, the inside walls of the container, then that's going to expand the container and the volume is going to increase, right? So higher temperature means more pressure by the particles because they're hitting the sides of the container with more force because they're moving faster, and therefore the volume of the container will increase, and vice versa. If you lower the temperature, the volume will decrease. So that's an explanation of Charles' law from the kinetic molecular theory. What about Avogadro's law? So Avogadro's law, you remember, is volume V1 over N1, V2 over N2. And so here we're relating volume with the amount of moles of gas, right? Here we were relating the volume with the temperature, and we were able to explain why they're directly proportional according to the kinetic molecular theory. Well, what about Avogadro's law? Why are they directly proportional? Well, this goes back to, again, think of a deflated basketball, right? So if I have a less air in the basketball, then the basketball will collapse, right? So less volume. Or you can think of a balloon as well, right? So if I have less air in the balloon becomes smaller, less volume, right? So if I put more particles in the balloon, right? So more particles in the balloon, I'm not changing the temperature, I'm just putting more particles in the balloon. Increasing the number of particles in the balloon causes more particles to hit up against the side of the container, more collisions on the side of the container at any one moment, therefore more force on the container, therefore more pressure on the container, and therefore the volume will increase. And then same thing with taking away air or particles from the container, right? So if I decrease the number of particles, less pressure, less particles hitting up against the container, therefore less pressure, and the volume will decrease. Okay, and then finally, we have the Dalton's law of partial pressures. What is Dalton's law of partial pressures? That says that the total pressure of gases, if you have a mixture of gases, let's say gas A, B, C, D, and so on, the pressure of the individual gases added up equals the pressure of the total pressure of all the gases mixed together. And the reason for that, again, is because according to kinetic molecular theory, all of the gas particles are separated from each other in such a way that they're not interacting with each other. They don't interact, and they're very far apart, so they will behave as if they are by themselves, right? So each gas will behave as if it's alone in the container. And so we could focus on each gas by itself, figure out what the partial pressure is, and then add those together, and that will be the total pressure. That's it for this video. I hope you enjoyed the video. If you liked the video, then please like the video, hit that like button, smash it. Also, share it with your friends. Make sure you subscribe to my channel, hit the notification bell, select all, and make a comment in the comment section. Thanks for joining me. Have a great day.